Thank you, Addie. So yeah, my name is Wesley Chambers. I work at Marshall Space Flight Center, and I am the deputy PI for this HLS risk reduction ground test that I'm going to be talking about today. I have kind of some introductory material that I'm going to go over that is going to be familiar to most of you, so I'll kind of gloss over it, but there are a few points that I would like to go ahead and make. So yeah, if we could go ahead and go to the next slide. Right, so most of y'all are familiar with the material here with the diagram showing how plume-surface interactions, how rocket exhaust interacts with the planetary surface. It has effects both potentially to the vehicle that's landing and to surrounding assets. The main thing that I just kind of want to point out here is that, you know, what we call plume surface interaction is kind of a colloquialism. You know, it's the specific subset of fluid granular physics that deals with spacecraft, you know, rocket exhaust interacting with unimproved planetary surfaces is maybe a more comprehensive way of saying that, but because that's a mouthful, we end up calling it plume surface interaction. But that really involves then, and I've shown in other places maybe a more complex Venn diagram. It involves people doing mission work. It involves science, you know, studying different planetary surfaces. It involves people doing mission design, concept of operations. All of these different factors go into mitigating, understanding, reducing risk to space missions. And so next slide, please. Those risks, again, are pretty well understood here. We know that all propulsive landers experience plume surface interaction. And as some of the speakers have already highlighted, you know, you can see the effects in changes in reflectance and things like that from orbital assets. We have seen that it can affect nearby spacecraft. So PSI has this, you know, it is a potential hazard to all space missions. And so understanding it better is essential to conducting successful missions, conducting successful near surface operations, to understanding how we mitigate the effects and mitigate not just the effects to the vehicle itself that we're landing, but to surrounding assets. Next slide, please. You may be able to tell that Ashley and I are co-authors here and working together on this because I may have borrowed this quote from her as well. You know, we haven't lost a lander yet, but we have due to PSI effects, but we have seen the effects on surrounding assets. We have seen damage to vehicles from PSI. And so inform where we're at today, but we also know that as we are going to larger landers, to, you know, the Human Landing System program, where we are kind of getting outside to some extent of our Apollo experience, we know that we need to better understand plume surface interactions and better understand the erosive effects and their scale and how different regimes interplay with these vehicles so that we can reduce risk to HLS. So new data and new modeling methods and maturation of the modeling methods that we have is needed. Next slide, please. This is also, you've seen this slide as well before. We have three different kind of approaches to reducing risk from plume surface interaction. I'm going to be highlighting today a test for HLS. But the reason we do that is this fits in between the flight data, some of those instruments you've heard about already, and that we'll be talking about again later. Tomorrow, we're going to be focusing on modeling and simulation, where we've talked about how it fills in testing and data gaps, but it also allows you to do more than you could do with just flight and experiment. Flight data we get, it's kind of a one-shot, if you will, per landed mission. You get ground truth, you get the actual effects in the environment of interest. Modeling and simulation, you can run a bespoke test, if you will, to understand something that you can't a situation you might not see. So we're sitting here in the middle with experimental data where we have better control. We can instrument things better than we could on a flight, where you're dealing with more obviously mass and weight restrictions and things like that. And we can try to tailor that test to be as accurate as possible to the environment of interest. So next slide, please. So HLS is taking astronauts back to the lunar surface. We're using commercial vehicles from SpaceX and Blue Origin. This is part of the Artemis program, as Sean was talking about earlier. Each one of these vehicles is larger, and it uses a different concept of operations than Apollo. And so the environments produced by these vehicles is going to be different. And you can see that we're dealing with a different environment with potentially less benign environments than we had during Apollo. So in order to study this, we are going to be conducting a test for risk reduction that will be exploring into these different environments with a scaled but larger than we've done before Plume-Surface interaction test in vacuum. Next slide, please. So overall, this test concept, our goal is to reduce risk to the HLS lander through acquisition of lunar relevant ground test data to quantify and reduce uncertainty in PSI predictions. The goal here is to conduct a vacuum Plume-Surface interaction test using a high fidelity regolith simulant, using a highly underexpanded plume that is relevant to human class landers. So we'll be able to vary nozzle height above the regolith. We'll be able to vary our plume pressure, total pressure, and mass flow rate. And we're going to be doing targeting 30 runs per propulsion type. And I realize I did not get a chance to our schedule has slipped a bit, but we'll be doing 2 tests, both with an ethane system. I'll talk about this in just a second, but an ethane system that is non-combusting, and then also a hybrid motor as well. Next slide, please. So we're going to be doing this test on the 60-foot vacuum sphere at NASA's Langley Research Center. So this was actually a facility that was used during Apollo and the Viking era to test Plume-Surface interaction. It's a very large volume. The goal here, obviously, in doing a vacuum test is one, to not just enable enable us to get a highly underexpanded plume, but also to minimize ambient pressure rise during Plume-Surface interaction testing. So we're going to be targeting a test condition of about 100 pascals or 750 millitorr. And you can see here the facility in these photos. It is quite large, and not only is the facility large, but also the accompanying hardware is going to be pretty big. This is something that we're going to be doing to get a relevant test with a large, highly underexpanded plume. Next slide, please. So in order to kind of parse out two goals here is, one, we want a highly underexpanded plume that matches the absolute peak pressure, but though it is radially scaled in, and that distribution that is kind of relevant to human class landers. And we're going to be trying to match our target parameters of interest really are pressure and shear. We're going to be doing about 4 to 6 seconds per test run, and we're going to be using 2 different systems. So each one of these systems offers advantages in terms of ability either to vary the test conditions of interest, to inform modeling, or in the case of the hybrid motor, it allows us to put water in the exhaust products. And that's something that will then let us compare to the non-combusting ethane rig compared to this hybrid motor. And so we'll be able to parse out not just sort of variance within a test, but also variance between tests to see how the exhaust products affect PSI outcomes. Next slide, please. For our lunar regolith simulant, we're going to be using BP1. This may be probably familiar to many of you, but it's a crushed basalt lunar regolith simulant with similar geotechnical properties to the HLS landing sites. Now, this is a basaltic simulant, so maybe more representative in a mineralogical sense of the lunar mare. But for our purposes in looking at geotechnical properties, is appropriate to, in terms of particle size distribution, particle morphology, to kind of the entire lunar surface. Plus, we were able to get it in sufficient quantities. We're going to be using about in the neighborhood of 1,800 kilograms of this material for our regolith bin that'll be about 2 meters wide. So getting a simulant that is representative of the lunar surface is really important here to understanding plume effects and PSI outcomes. So we've been partnering with our colleagues at Kennedy Space Center to develop preparation techniques and handling techniques and how to get that much regolith into the bin for use for this test. Next slide, please. So instrumentation diagnostics, we're doing this, but what is really important to this test effort is the data products that we're going to get out of it, is those data that we can then use to better understand and integrate and use to be input into PSI modeling efforts to better understand and reduce risk to the HLS vehicle. So we've got both primary and secondary instrumentation focused at erosion and ejecta. We are going to be using SCALPS, which you'll be hearing more about later. But SCALPS is a stereo camera system that will be used to capture the surface, the surface morphology in our regolith bin, both before the test, during, as it's actively eroding to as best we can during that PSI event, and then the surface after. So that will allow us to reconstruct how much material was lost. It'll allow us to see the transient ejective sheet, and then be able to back out what the erosive effects for each test are. We'll also be getting ejecta energy measurements from, we've got a radar unit and a dust concentration monitor from our colleagues at Kennedy Space Center. So we'll be able to get and understand sort of the ejecta velocities and energies that are being generated by each PSI test. Alongside that, really important for context is getting facility pressure, getting the plume visualization that will allow us to verify our flow conditions. We'll also be measuring the surface pressure and shear generated by each plume using a flat plate, so that we understand and can correlate those pressure measurements directly to the test outcomes. Beyond this, we also are going to have some passively collected data for dust, witness plates, coupons, mechanisms. We recognize that this test is really just the environment that we're creating is really unique. Testing like this doesn't happen that often, and so we've been partnering with the dust mitigation community as well to make sure that we can take advantage of this environment and make sure that the test is as valuable as possible. Next slide, please. So in terms of using these data for risk reduction, at the very beginning, we're going to be getting data and we'll be able to make a qualitative comparison. When we get these results, we can go and say, hey, are the environments we're seeing, does this give us a clue to whether or not we're outside our Apollo-informed experience for landing? And then as we go, we can basically take that and then incorporate these data into sort of higher fidelity models as needed to answer the question about risk to the vehicle and determine, basically that we can reduce risk to the vehicle for safe crewed landing. Next slide, please. So in summary, PSI, it produces risks, or it poses risk to all propulsive landers, as well as surface assets and to nearby infrastructure. This is something we'll kind of be discussing later on in the breakout sessions. You have both your, risk to the vehicle, and then there are far field effects. This PSI test is geared to reduce risk to the HLS lander because it's something we're kind of moving again from our Apollo experience into new, potentially less benign environments. And this is really a unique opportunity. The last time we had PSI testing of this type at this scale, was conducted in these vacuum facilities during Apollo. And so this is something we're really looking forward to seeing how this testing will inform and reduce risk to the HLS lander to enable safe crewed landings. So with that, be happy to take, well, may not have time for questions, so I'll try to address things in chat.